Okay, let's talk about escape velocity. Now, here's what we know so far. This is what we did. We've got the Earth, the moon's way out here, and the Apollo 15 spacecraft went into orbit, a very low Earth orbit, around the Earth like this. They go around one time. Now, we already talked about orbital velocity. We said that the orbital velocity is equal to the square root of g(m) over r. Now, this is the mass of the Earth, if we want to escape from the Earth. This is the radius of our orbit, and this is the universal gravitational constant. Okay. Now, what we want to do is we want to get to the moon, and in order to get to the moon, we need to escape from Earth's gravity. So we need to go faster than this. So you fire your engine. It had an engine on it. It fired for a few minutes, and it increased its velocity enough so that when it would leave the Earth, it's still being slowed down by the Earth, right? You're going this fast. So, I mean, you're leaving the Earth towards the moon, and what happens is that as you move away from the Earth, what happens to gravity? It gets weaker. Now, it's still there, and gravity is slowing you down. So you go, and actually it turns out to be 25,000 miles per hour when you leave low Earth orbit. You go 25,000 miles per hour. Now, gravity's going to slow you down, right? So as you move away from the Earth, you're slowing down. But gravity is getting weaker. So what happens is that if you go just the right speed, you'll never quite stop. Gravity will never be strong enough to make you stop. You'll always, in fact, when you get infinitely far away from the Earth, that's when you'll stop, but you'll never get to infinity. So that's what we want to figure out, is how fast do I need to go so that I'll go up and never come back down. So I can escape from Earth's gravitational field. Well, here's what you need to know. You need to know that, and we derived this in yesterday. We said that the gravitational potential energy, if you're using for planetary applications, is equal to negative g(m)m) over r. Negative because we're actually said that gravitational potential energy at infinitely far away, is defined to be 0. Well, you're always below infinity, right? I mean, if you look up in the sky and you say, wow, infinitely far away. Well, nobody's infinitely far away. So you're always below infinity. And if you're below infinity, if you're beneath where you said gravitational potential energy is 0, then you're always going to have negative gravitational potential energy. Okay. Now, we're going to use this concept now to derive an equation for escape velocity. And it's a little bit involved, okay? But let's take a look at a really simple case, okay? Well, let's see. Suppose I finally had it with Gannon, okay? He's just asked me one too many questions, and so imagine here's the surface of the Earth, okay, flat surface, and here's a well, and so we throw Gannon down to the bottom of the well. Okay. Yes. Okay. So here's Gannon down here at the bottom of the well. So yes, true. Now, Gannon, he survived the fall, and he's a pretty resourceful guy, so he wants to get out. So what he does, he finds a rock. There's a little rock at the bottom, and he has a little Post-it note. So he writes, I don't know why, but he writes a little Post-it note. Help! Get me out of this well, and arrest Lake. All right. So he puts that on a rock, and so tapes it or posts it to the rock, the note, and he throws the rock straight up. Okay. Now what he wants to do is he wants to throw the rock fast enough to get out of the well. Right. What happens if he throws it too slow? Right. It'll go smack. All right. So then he's out for a couple hours and wakes up, says, okay, I got to throw it harder. Now, you could throw it so fast that it goes like this. way out of the well, right? Okay, way faster than you need. So it did escape from the well. It did escape from the well by throwing it too fast. But, you know, we know Gannon, right? He wants to get out of the well with as little effort as possible, right? As little work as possible. So, what he'll do is he'll say, I need to make a calculation. What speed do I need to throw so that just when it gets to the lip of it, it stops and just lands right there on the lip? So what's the minimum speed I need for that rock to go all the way up here and then land right there? That minimum possible speed you need to escape from the well is called the escape velocity. Now we know how to do this. Let's take a look at what is the mechanical energy. Remember mechanical energy? Mechanical energy is our kinetic energy plus our gravitational potential energy, right? Now, what is up here, what is our kinetic energy right here at the very top? What did we say happened to the rock right when it got to the very top? It stopped. So what's our kinetic energy if it stopped? Zero. It's zero. And then our potential energy. Well, what is our potential energy if you're here on the ground? Zero. Well, it all depends on what you want to make it. But we're going to say that we're going to define potential energy to be zero right here. So this is zero. So our gravitational potential, so the rock right here has zero mechanical energy. Okay? Because in most countries, 0 plus 0 equals 0. All right? Now this is the final mechanical energy of the rock. But look, when the rock left Gannon's hand, the only force doing work on the rock, the only force slowing the rock down was gravity. So as the rock went up, it lost kinetic energy, but it gained potential energy, right? And we said that, hey, if gravity is the only force doing work on an object, then mechanical energy is conserved. You just have to believe that. E initial equals E final. Because gravity is the only thing slowing this rock down. Now, we covered that, several units ago, so go back. If you've forgotten why this is true, go back and look at those notes. But just accept it for right now. E initial equals E final. Well, if that's true, then E final is 0. Well, that means E initial has to be equal to 0. But look at the energy that this rock has. It does have velocity, doesn't it? So E initial does equal, it's got kinetic energy, right? Well, what is kinetic energy? 1/2 mv squared, right? Let me zoom in. But it also has, K plus, it does have potential energy. But if our potential energy is 0 right here, what is it down here? Do you see that we're below 0? We're below our reference. So the rock that he's throwing at the point, at the bottom of the well, it had negative gravitational potential energy. So that's because mg, right? We said that potential energy is mgy, right? In a uniform gravity field. mgy, but look, y is negative. It's negative y. Or this is our depth below the surface. Well, this allows me then, because this is negative and this is positive, it allows this to add up to 0. Right? But if this is 5 joules, this would have to be negative 5 joules. And 5 plus negative 5 is 0. Woo! Well, this allows me now to solve for the escape velocity from this well. So this well, we would say, well, 1/2 mv squared. Just add this to both sides is equal to, well, this is all equal to 0. So add this over there is equal to mgy, where y is our depth below the surface. The mass of the rock doesn't matter. Multiply both sides by 2 and take the square root. And the escape velocity from this well is the square root of 2gy. Okay? But this is not the escape. No, this is the minimum velocity that Gannon would need to throw that rock so that it can leave the well. Does that make sense? If he throws it slower than this, it's not going to escape. It's going to fall back down. If he throws it faster than this, it will escape, but he threw it faster than he needed to. Okay? Is everybody with me on that? Okay. Now we're going to get to something that's very, very cool. When you're a rocket in low Earth orbit and you want to achieve escape velocity, think of the Earth as being deep in its own gravity well. Sometimes they'll say Earth is in a gravity well. When we're here on the surface of the Earth, we're at the bottom of Earth's gravity well. And to get up, into space, we have to climb up. Just as Gannon would have to climb out of this well, to get away from Earth, we'd have to climb out of Earth's gravity field. So this is the Earth right here. Just show it right here. Here's the Earth. Think of the Earth as being at the bottom of a gravity well. But instead of showing the well like this, I'm going to draw the well like this, like it's a curved path. Now, why is that? Well, see here, we assume that gravity was uniform, 9.8 newtons per kilogram. But what do we know is true about gravity as you move away from the Earth? It gets weaker. So we're going to show that by showing the slope, like it's getting easier and easier to climb out of this gravity well. Now what we want to do from low Earth orbit is launch our rocket, increase the speed of our rocket, so that the minimum possible speed so that we'll get out of Earth's gravity well. Which means that when I leave the Earth, when I go way out here, billions of miles away, my velocity will approach zero. Now, it'll never reach zero, because if it ever does reach zero, now Earth's gravity can pull it back. But if it never quite reaches zero, if the velocity of our rocket only approaches zero, right? Because, look, gravity is slowing it down. We leave at 25,000 miles per hour, but as we leave the Earth's gravity is pulling down on us, and it's slowing us down, okay? But as we move away, it's slowing down, slowing down, slowing down, slowing down, slowing down, so that when R gets to infinity, when our distance from the center of the Earth, as it approaches infinity, right? We never get to infinity, but we can go really, really far away. Then our velocity will go to zero. Well, let's take a look at what mechanical energy is way out here. E is equal to K plus U. But now this is equal to 1/2 mv squared. That's still true. But what is gravitational potential energy now? If you're talking about a gravity field that's decreasing, well, it's negative gmm over r, right? So this is plus negative gmm over r. Well, what is this equal to is if I go really, 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 really far away, then velocity is approaching zero. Well, if velocity is approaching zero, what is this going to? 1/2 mv squared. If the velocity is going to zero, this is going to zero, yes? So our kinetic energy is going to zero. And as r goes to infinity, what happens when you divide by something that's going to infinity? You remember from AMA?
Zero, right?
It goes to zero. Yes, because when you divide by a humongously huge number, you get a teensy-tiny answer. Your answer is going to go to zero. So while this goes to zero, this also goes to zero. This goes to zero. And something that goes to zero plus something else that's going to zero is going to zero. So E final, when you're really super far away, we can say essentially is equal to zero. But look, once you shut the rocket down and have achieved escape velocity, the only force doing work is the force of gravity, which means that E initial is going to be equal to E final, which is equal to zero. Which means that E initial. Now look, here we're not going 0. We're going 25,000 miles per hour. That's what it turns out to be. Really, really super fast. Lots of positive kinetic energy. 1/2 mv squared. Okay. Plus, right, because mechanical energy is kinetic energy plus gravitational potential energy, negative gmm over r. But this is equal to 0. So look what I can do. I can solve for v. I can solve for the velocity. What velocity makes this true? Well, notice the mass of our spacecraft cancels out. Then you add this to the other side. So you have 1/2 v squared equals negative gm over r. Oh, wait, add it to the other side so it becomes positive. Multiply by 2, gets rid of that, and then take the square root. So our escape velocity equation, v escape, the one that we want, is equal to the square root of 2 gm over r. This equation tells you how fast you need to go so that you'll go up and never come down. Now, if you're here on the Earth's surface, if you want to throw a baseball up so that it will never come down, it turns out when you plug in all these numbers, and this right here would be the radius of the Earth, right, because you're on Earth's surface, and this is the mass of the Earth, big G, and it turns out to be about 26,000 miles per hour. You do not want to try to throw a baseball 26,000 miles per hour because you'll die. Well, you'll hurt your arm real bad. But the baseball will crunch in front of the air, compressing the air, heating the air, and it will heat the air so rapidly that that heat will flow, right? Heat flows. It will radiate into the baseball and into you, and poof, you will vaporize like a meteor falling through space. Okay, not good. If you want to go this fast, you need to be in space, outside the atmosphere, because you can't go this fast inside the Earth's atmosphere.
So, and how fast does light travel?
Well, light travels much faster than this. Yeah, so it's not even.
So, like, theoretically, we could never achieve light speed because we'd die.
Oh, not in the atmosphere. And you can't achieve light speed because it would take more energy than there is in the universe to do it. That's a whole different lecture. That's relativity. It's cool, though. It's very cool, but it's beyond the scope of this lecture. So this is our escape velocity equation. So let's summarize now everything you need to know about. Oh, wait. There's one cool thing about this. Let me zoom out. What's the orbital velocity equation?
Square root of gm over r.
And look, here we got a square root of gm over r. So we can express the escape velocity equation in terms of the orbital velocity. The escape velocity is equal to what? Times the orbital velocity. 2? Think. Look at it carefully. Square root of 2. It's the square root of 2 times the orbital velocity. What a cool universe we have. The escape velocity from the planet is equal to the square root of 2 times the orbital velocity. Isn't that amazing? Why the square root of 2? It's because of the nature of three-dimensional space. We live in a three-dimensional universe, and gravity spreads out by the square of the distance, and so all of that forces our universe to exist in such a way that the escape velocity, to go up and never come down, is equal to the square root of 2 times the orbital velocity, the velocity you need to do to fall around a planet. Very, very cool stuff. So to summarize, oh shoot, hold on. I've got it right over here.
We took notes.
Now this is what you need to write down. Okay, and then, yeah. Okay, so if you write all this stuff down, you can do the one last assignment I'm going to give you, and you'll be able to do the quiz I'm going to give you. The assignment's worth 5 points. The quizzes will be worth 15 points, for a total of 20 points. And remember, that's what life is all about. It's about points. especially when you get married. All right. Now, so here's the equation for the force of gravity. You need this. The orbital velocity equation, the potential energy in gravity fields above planets, the escape velocity equation, both in square root of 2 gm over r, and then square root of 2 times orbital velocity. You need to know that mechanical energy is kinetic energy plus gravitational potential energy. And of course, kinetic energy is 1/2 mv squared. Then you need to know this. One thing I showed last class that I didn't show you, that if we are at escape velocity, if you are at escape velocity, you have zero mechanical energy. Everywhere you go, you have zero mechanical energy. Now you have positive kinetic energy, but you have negative gravitational potential energy, and they will add up to zero. So you can say, oh, okay, well, k plus u equals 0. That means k equals negative u. Well, negative gmm over r, that means, hey, my kinetic energy is actually equal to gmm over r. Kind of cool. More cool stuff. And then these are the values you need. This is the radius of the Earth, and this is the mass of the Earth. This is the radius of the moon. This is the mass of the moon. And this, of course, is the gravitational constant. So you need all that stuff to do the problems. So good luck with the problems. Goodbye.